The search for life beyond Earth has never followed a straight path. It advances in uneasy steps, guided less by optimism than by surprise. Time and again, our instruments have shown us places that should be dead, frozen, or chemically hostile, yet stubbornly refuse to fit those expectations. In 2015, when NASA's Dawn spacecraft slipped into orbit around Ceres, the largest body in the asteroid belt, scientists expected to confirm a simple story. Ceres was small, ancient, and cold, a relic left over from planet formation. What they found instead was a surface punctured by more than 100 brilliant white scars, glowing against dark rock like deliberate signals. The brightest of these lay within Ocketer Crater, where a 15-kilometer-wide region reflected sunlight with startling intensity. Analysis revealed sodium carbonate, a salt that on Earth forms when warm, mineral-rich water circulates underground and later evaporates. Its presence meant that Ceres once hosted liquid water beneath its crust, possibly far more recently than anyone expected. Even more unsettling was the haze that appeared and vanished above Ocketer in rhythm with Ceres's day. This mist suggested ongoing sublimation, water vapor still leaking from below, hinting at briny reservoirs trapped beneath the surface of a body that should have been frozen solid for billions of years. That same pattern of defiance appears again and again as we move outward. Saturn's moon Titan looks alien at first glance, with methane seas and hydrocarbon rain. Yet gravity data from the Cassini mission revealed something deeply familiar below its icy shell. Beneath 50 to 80 kilometers of ice lies a global ocean of liquid water, hundreds of kilometers deep, mixed with ammonia that keeps it from freezing. This ocean likely touches Titan's rocky interior, enabling chemical reactions that mirror those thought to have sparked life on Earth. Above it, complex organic molecules constantly fall from the atmosphere, accumulating on the surface and possibly filtering downward through fractures in the ice. Titan is also wrapped in protection, shielded by a thick atmosphere and Saturn's magnetosphere from cosmic radiation. If life ever took hold in its hidden ocean, it would have had billions of years to evolve in stable, isolated conditions. Mars, long considered a dead world, tells a similar story in darker tones. In 2018, radar data from Mars Express revealed a bright reflection beneath the south polar ice cap, consistent with liquid water buried 1.5 kilometers below the surface. The temperatures there are brutally cold, far below the freezing point of pure water, but extreme concentrations of salts can keep brines liquid even at minus 68 degrees Celsius. Subsequent observations showed multiple lakes, forming an interconnected system beneath the ice. These environments are harsh beyond imagination, hypersaline, dark, and isolated. Yet on Earth, microbes thrive in comparable extremes. If Mars ever hosted life during its warmer past, these subsurface brines may be the last places it could survive, hidden from radiation and the thin, hostile surface above. Taken together, these worlds force an uncomfortable conclusion. Liquid water, once thought rare and fragile, appears again and again in unexpected places, sustained by chemistry, salt, and hidden heat. The question is no longer whether water can exist beyond Earth, but how often it does, and what it might be quietly sheltering. As we venture farther from the sun, the persistence of internal heat becomes even harder to ignore. Neptune's moon Triton, captured long ago from the Kuiper Belt, should be a frozen fossil. Its surface temperature hovers near minus 235 degrees Celsius, cold enough to lock all activity in place. Yet when Voyager 2 passed by in 1989, it witnessed geysers erupting nitrogen gas and dark material kilometers into the sky. Triton's backward orbit around Neptune creates intense tidal stresses, flexing its interior and generating heat through friction. Models suggest that beneath its frozen nitrogen crust lies a subsurface ocean of water mixed with ammonia, kept liquid by this tidal heating. Triton may exist in a fleeting window, warm enough for liquid water now, but destined to be torn apart by Neptune's gravity billions of years in the future. Uranus's moon Miranda presents an even stranger case. Barely 470 kilometers across, it displays a surface that looks shattered and reassembled, with towering cliffs and oval regions of chaotic terrain. Such violent geology demands energy that a body of Miranda size should not possess. The leading explanation is an ancient orbital resonance that once subjected Miranda to extreme tidal heating. What unsettles scientists is how fresh some of its features appear. If residual heat still lingers within, Miranda could harbor isolated pockets of liquid water trapped among fractured ice, a labyrinth of frozen blocks and hidden chambers created during its turbulent past. Then there's Iapetus, Saturn's two-toned moon, marked by a colossal ridge running almost perfectly along its equator. Rising 20 kilometers high and stretching 1,300 kilometers long, the ridge defies easy explanation. Hypotheses range from collapsed ring systems to ancient tectonic forces, but none fully account for its precision. While speculation about artificial origins remains firmly outside mainstream science, the fact remains that natural explanations are incomplete. Whatever formed the ridge likely involved internal processes we do not yet understand, processes that may have once reshaped Iapetus from within. Europa, Jupiter's icy moon, brings these questions into sharper focus. Beneath an ice shell 10 to 30 kilometers thick lies a global ocean containing more water than all of Earth's oceans combined. Jupiter's immense gravity needs Europa's interior, providing constant heat, while the thick ice shields the ocean from one of the most intense radiation environments in the solar system. Observations of water vapor plumes and salts suggest hydrothermal activity on the ocean floor, similar to Earth's deep sea vents where life thrives without sunlight. Europa's ocean has existed for billions of years, isolated, stable, and chemically rich, an enormous hidden environment with all the known ingredients for life. Each of these worlds tells the same unsettling story. Size, distance, and surface conditions do not determine habitability as cleanly as once believed. Where there is heat, salt, and water, even in darkness and cold, complexity has room to grow. The evidence becomes almost impossible to dismiss when we reach Saturn's moon Enceladus. Cassini's discovery of towering plumes erupting from its south pole transformed speculation into direct sampling. Flying through these geysers, the spacecraft detected water, salts, organic molecules, and, crucially, molecular hydrogen. On Earth, hydrogen of this kind is produced when hot water reacts with certain rocks at hydrothermal vents, releasing chemical energy that sustains entire ecosystems. Enceladus also ejects tiny silica particles that form only at temperatures above 90 degrees Celsius. Together, these findings point to active hydrothermal systems on the ocean floor right now. Enceladus is not merely a candidate for habitability. It appears to host the same processes that gave rise to life on Earth, operating today beneath its icy shell. Ganymede, Jupiter's largest moon, adds another layer of complexity. It possesses its own magnetic field, generated by a molten core, creating a pocket of relative calm within Jupiter's radiation-dominated environment. This magnetic field also revealed the presence of a deep, salty ocean, likely hundreds of kilometers below the surface and more massive than Earth's oceans combined. Shielded by layers of ice and magnetism, this ocean has existed in stable isolation for over 4 billion years. If life arose there, it would represent an entirely separate origin, biology born and evolved without any connection to Earth. Finally, we return inward to a world long dismissed as utterly inhospitable. Venus, with its crushing pressure and searing surface heat, seems the definition of lifeless. Yet high above that inferno, in the cloud layer 50 to 60 kilometers up, conditions are surprisingly mild. Temperatures and pressures approach those at Earth's surface. In 2020, the reported detection of phosphine gas in these clouds ignited controversy and debate. On Earth, phosphine is closely associated with anaerobic life, and no known non-biological process produces it easily under Venusian conditions. The detection remains disputed, but it exposed a deeper truth. We do not fully understand Venus's atmospheric chemistry, and we have barely considered the possibility that its clouds could host life. Unknown particles absorb ultraviolet light in those clouds, creating dark patterns still unexplained. Some researchers cautiously suggest microbial life as one possible explanation among many. If life exists in Venus's clouds, it would shatter long-held assumptions. It would show that life can persist in acid, float in the sky, and adapt to conditions we once thought fatal. More unsettling still is the proximity. Venus is our nearest planetary neighbor. If it harbors life, then alien biology has been close all along, overlooked because we assumed we knew where life could and could not exist. Across asteroids, moons, planets, and clouds, a pattern emerges. Life may not require gentle surfaces or familiar skies. It may only require chemistry, energy, and time. The universe keeps offering reminders that our assumptions are narrow, and that the places we once dismissed may be the ones most alive with possibility.